everyone. I'm here today to present adversarial testing with reinforcement learning, which is my research topic in my PhD that I am investigating with Professor Paulo Tonella and Dr. Matteo Biagiola. Okay. So nowadays we see that autonomous driving systems, also called ADSs, are becoming a reality. But they are safety critical by nature, by definition, because they deal with human lives and the environment in general. And because of that, they need to be accurately and robustly tested before the deployment. However, how to test them is still an open research challenge. The techniques presented in the literature, they manipulate virtual environments such as simulators in order to cause a perturbation and finding a failure, such as a collision, not only a collision, but it can be, for example, a collision. And when we look to the problem like that, we can look at it as an optimization problem, where the goal is to maximize or minimize an objective function, such as a distance to a misbehavior. And then we can apply reinforcement learning to solve this problem, to try to solve this problem. And why reinforcement learning is suitable to this kind of problem? Because it's a technique that allows the agent to learn with the interaction, from the interaction with the environment, and it deals with sequential interactions at runtime, step by step. And because of that, it could dynamically test the behavior of autonomous driving systems. And what we need when solving a problem with reinforcement learning. So reinforcement learning is a learning paradigm with the goal of learning a policy map states into actions to maximize a reward specifically. So we have the agent, we have the environment, and the agent will perceive the environment through states and select an action considering it. And then this action will take the environment to the next state, and the environment will give to the agent a reward, which is a feedback signal to guide the agent towards the objective of learning this policy. Okay, using reinforcement learning to test autonomous driving systems is not new in the literature. We can find some works, and they're normally split in two categories, separated in two categories. One with the centralized controller, and one that we call unrealistic adversarial agent. One example of a centralized controller is the work of Molo, when they use where they use reinforcement learning and many objective search in order to find test cases where the agent violates as many requirements as possible. And which are the requirements in this case? For example, follow the center of the lane, avoid a collision, respect the traffic light, and reach the destination on time. We call it centralized controller because it can control the entire environment, including aspects such as the vehicle in front, the light intensity, the weather intensity, or even some pedestrians that occur. Here we have an example of a failure that can occur with this type of environment. Here we have the vehicle in front, not sure this, and we have the vehicle under test, that is this other one. This is a failure that is possible, but it's not the most interesting type of failures because these type of failures cannot be avoided. The agent needs to follow the requirement of following the center of lane, and the vehicle in front is just crossed in his way in a way that he cannot avoid. Okay. As an example of a realistic adversarial agent, we have the work of Bezanda and Munir when they train, where they train an optimal adversarial policy for ADS with the goal of causing direct collision between the ego, the one that is being tested, and the adversarial ADS, the one that is defying the ego. And here we have some frames of the type of failures that is found in this environment. Two observations regarding this part. One is that the adversarial agent does not drive very well because, as you can see here and here, it goes like this. As pretty much seems like when we are playing some video games of Need for Speed, for example, the ones that are from this time, and so on. And the type of failure that it causes is like this. It came from behind and hits the ego vehicle in a way the vehicle cannot avoid. Okay? We call this type of direct collisions invalid failures because they are caused by purely adversarial behavior. Okay, although they contribute to the field, when we are focused on these more, how can I say, these more limited type of failures, which is more main focus on crashing, more subtle failures can be skipped, can be unnoticed, and these are the ones we are interested in the most. So because of that, our research goal is to train an adversarial agent for EDS scenarios that is fully autonomous. We don't want a centralized controller. We want an agent that controls the car, is fully autonomous, that challenge the ADS on the test, but that minimizes purely adversarial behavior. We want to find these failures that are not so obvious, let's say this way. Okay? And this is the approaching we are proposing. It takes as input an autonomous driving car that already knows how to drive. So it knows how to drive, you want to test it, and it uses this agent that knows how to drive to train an adversarial ADS. So here in this training phase, the agent does not learn, doesn't need to learn how to drive well, it already knows. It needs to learn how to act in a way to defy the ego agent. So the output of this first step is an adversarial ADS that learned how to defy this ego ADS. But once we have this agent, what should we do? How can we use it to improve the ego, which is like the main goal, let's say this way. So we have the second step, which is the fine tuning, when we put the ego ADS together with the adversarial ADS, learning how to avoid the behavior of the adversarial. And as a result of this loop, we have an improved autonomous driving system. Okay. And in order to investigate whether this approach is valid or not, we decided to go for a case study, what we call in an environment called Highway EMV. So this Highway EMV is an open AI gym focused on autonomous driving. Open AI gyms are very used for the evaluation of reinforcement learning algorithms. And as you can see, you have here the ego, the vehicle under test, and one vehicle in front. For this environment, we have as a space the observation that the agent gets from the environment, the position and the velocity of both vehicles in both axes, X and Y. And we have the action space, the possible actions that both of them can make. 5-1, idle, stay the same, nothing changes. Going left, going right, go faster or go slower. Considering this environment, we have two different rewards, and the reward for the part of the reinforcement learning is the most critical one, because it's the component that will guide the agent through the task of learning. And we have one for the pre-training and fine-tuning reward that is focused on, we call it quality of driving, and reward the vehicle if it goes as fast as possible without causing collisions. And we have the adversarial reward for the adversarial training phase that reward the adversarial agent, when it drives well, when it keeps a closer distance with the ego because the probability of a collision increases, and when it causes a collision in fact. Okay, this one is given by the environment we are using, and this one is part of our contributions to this topic. So going a little bit more in these two rewards. First, in the quality of driving reward, we take into consideration 3 different components. If it going in high speed, as I said, and if a collision occur in the right lane one. And we have these weights here that will vary. So for example, we want the vehicle to go in high speed. So the vehicle, the reward has a positive weight. But in case of collision that we don't want it to happen, it's a negative reward because we're penalizing it every time it occurs, at least in the pre-training and the fine-tuning phases. And then we have the adversarial training reward that is split in 2 different components. One is given to the agent at each time step, and the other is given to the agent at the end of an episode. For the one that is given to each time step, it considers the quality of driving, the one that I introduced before. But here, since we want a collision to be caused, we set the weight of the collision to 0. And it's also considering the difference, the distance difference between the 2 vehicles. And for the episodic one, it's basically summing up all the rewards of each step, and it gives to the agent just in the case of a collision occur. And this is the reward that we're also introducing here is the difference, the distance difference, and we consider three different aspects: the distance between, the difference of the distance of the velocities of between the vehicles, and the Euclidean distance between them. So velocity and distance between them. Why? We have three different components. The first one component penalize the agent, gives a negative reward if the adversarial is going far away from the eagle. You agree with me that if the adversary is going far away from the eagle, there's no chance that a collision occur. So it's a negative reward. The second component, it also gives a negative reward if there is a changing of lane, because the vehicles, they are in the x-axis in the same position, but in the y, in different one, the collision can occur. But even if they are in different collisions, in different lanes, the collision can still occur, so we penalize it, but not as much as in the first case. And the third case is basically the reward that we give when the two vehicles are getting closer, and it's the inverse of the distance. It's a positive reward. So first case negative, second case negative, third case is positive. Okay? And then considering this environment and this reward, we wanted to analyze two things. One, regarding the failure exposure, we want to know how effective in causing collision this approach is. And the second one is regarding the fault repair. And we want to check if the Eagle ADS improve after retraining in the presence of the adversarial ADS and how much. To analyze that, we conduct an experiment with three phases: the Eagle pre-training, the adversarial training, and the Eagle fine-tuning. The first case, the Eagle pre-training phase is not mandatory, but for this environment specifically, we didn't have an agent that already knew how to drive, so we needed to train it as well. And in order to do that, we put the Eagle in training mode, learning how to drive well according to the quality of driving reward, with a rule-based agent controlled by the environment. In this phase, we train the Eagle 10 times. We test each one of them 10 times. We pick the best, and we take the best one for the next phase, which is the adversarial training. In the adversarial training, we set the Eagle to the acting mode, so no learning. The Eagle is not learning anymore, just reacting according to what it learned before. And the adversarial is learning how to challenge the Eagle according to the adversarial reward. Here as well, we have 10 adversarial models trained. Each one of them tests 10 times, and then we pick the best and take to the next phase, the Eagle fine-tuning. And the Eagle fine-tuning, once we have the adversarial, we put the Eagle again in training mode to learn how to avoid the adversarial behavior, considering the quality of the driving reward. Is that mine or is that? Okay, sorry. Again, here we train it 10 times. We tested each one of them 10 times, and we use as metric the failure rate. So we want in the Eagle pre-training and the Eagle fine-tuning the failure rate to be small, and we wanted it to increase after the adversarial training, okay? And these are the results that we have. So after pre-training, the failure rate drops to 0.01, which means that the agent learned in this first phase how to drive well. And after the training, the adversarial training, it increases to 0.91, which means the adversarial learned how to make the Eagle crash. And answering our first research questions, which is regarding the failure exposing and how effective in causing collision our approach was. We compared with a random that is 0.09, so it was good. And then for the second part, the fine-tuning, this failure drops to 0, which means that the Eagle agent, after the retraining, the fine-tuning, learned how to avoid the adversarial behavior of the adversarial agent. Answering our second research questions regarding the fault repair. But we are curious.
I'm Siri.
Hello, Siri. So yeah, after seeing this result, we are curious about two different things. One is regarding the types of failures that this approach could cause, and the second one is regarding the zero, which was pretty much suspicious. So we took a look at the types of failures that our approach was causing, and here I have an example of the two of them. In the first scenario, the adversarial, which is the one in pink in front, is mimicking the behavior of the ego vehicle and causing a collision. And the second part is like switching lane very dangerously in a way that causes a collision for the ego, makes the ego to collide. And regarding the zero, we first observed what was happening and we see nothing. So we're not understanding what's happening, and we decided to do an analysis regarding the velocity. And what we noticed is that basically the ego learn a very conservative behavior after the retraining. So in this scenario, the highway, there is a minimum velocity possible, which is 20, and a maximum velocity possible, which is 30. So we see that after the pre-training, when the vehicle, the agent learns how to drive, we have basically considering the time steps, the velocity of the ego goes to the maximum. And then when you go after the first step, the adversarial one, we see that both of them start high, and then it comes down because it's when the crashes occur. And then in the last step after retraining, we don't even see the difference between them because they started in between 20 and 25 and they go to the minimum. So basically, the ego is learning how to keep the maximum distance possible from the adversarial, because the adversarial, even if it tries to go slower, it just can't. So they keep going in the same velocity. It was not the results that we were expecting at first, but it makes any sense since it's adversarial behavior in the vehicle. It is learning something indeed. This work that I presented here resulted in a publication in ICST, a software testing conference that will happen in Toronto in May. Okay, and I think most important, after this work, some questions arise and we are investigating them right now. So the first one is whether the proposed approach is generalized to other driving scenarios, because the one that we have is basic. So we are working right now to apply it to different scenarios. We are working right now on the intersection scenario. And the second one is to what extent are the failures found by the adversarial ADS valid. As I said before, we want to help improve the agent, the driving of the agent. So if you have unavoidable failures, it does not help anything, and it does not enhance the quality of the ego at the end. So we are working now to create a mechanism to automatically flag this kind of failures and identify how many of our failures are from this group are valid or not. And the third one is regarding the diversity of failures created by the adversarial ADS. Causing a lot of failures is good, but if all the failures are the same, our approach is not that much efficient. It's efficient, but it can be more. But it finds different types of failures. It's a more efficient approach. So we are working to, after being able to discard these invalid failures, our idea is to collect the trajectories of the vehicles and using some clustering algorithms such as K-means, for example, to figure out the diversity of failures. And we expect in the future to submit the extension of this work that we have been collecting with these new enhancements to a journal. Okay. So with this, I finish my presentation today. Thank you for the attention, and I'll be ready to answer questions.